Binary star systems host some of the most exotic worlds in the galaxy. The double suns of eternity takes you to planets that orbit two suns, where days stretch into twin sunrises and seasons flip under dual light. See how gravity, heat, and light choreograph climates and oceans in ways that a single-star world could never foresee. Crisp visuals and clear explanations pull back the curtain on how two suns shape weather, tides, and the potential for life. If you've ever wondered what skies look like under two suns, this journey is your front row seat. Binary stars and orbital dynamics. Binary star systems are common in the galaxy, and when planets join the dance, they follow two clear orbital archetypes: planets that circle one star, S-type, and planets that orbit around both stars, P-type or circumbinary. The gravitational center of such a system is the barycenter, a balance point around which both stars orbit. In a circumbinary arrangement, the planet's path wraps around this moving center of mass, while in a circumstellar arrangement, the planet hugs the gravity of just its primary partner. Planets in these settings experience a continuously changing gravitational tide as the binary stars orbit each other, which makes their orbits subtly more complex and often more constrained than around a single star. The dynamics hinge on how the binary's orbit and mass distribution perturb a planetary orbit. The potential is not static. It shifts as the two stars dance, so a planet feels a time-varying tug that can shape its eccentricity, tilt, and precession. There is a practical stability boundary. Planets that orbit around both stars must lie outside a critical region close to the binary, where perturbations are too strong to keep a steady path. How far out this boundary sits depends on the binary's separation, its eccentricity, and the mass ratio of the two stars. In general, circumbinary planets need to reside well beyond this inner edge to remain dynamically stable over long times. The opposite case, planets orbiting just one star, is usually more resilient but still sensitive to the companion's gravitational reach through resonances and periodic nudges. A small handful of well-studied systems illustrate these concepts. Kepler 16b is the archetype of a circumbinary planet, orbiting the pair Kepler 16a and b in a clear P-type path that demonstrates how a planet can coexist with a binary star in a single, coherent orbit. The Kepler 47 system takes the idea further with multiple planets circling both stars, showing that planetary families can form and persist in circumbinary disks. Observationally, detecting these worlds challenges traditional methods. Transits can occur in complex patterns because the host stars move, and radial velocity signals are blended with the binary's own motion. Yet transits have revealed that circumbinary planets can be common enough to warrant statistical studies, and they help refine our understanding of how binary geometry collides with planet formation. Disk dynamics and planet formation in binary environments add another layer of nuance. The inner regions of circumbinary disks are truncated by the star's gravity, creating a cleared zone that planets must migrate into from farther out. Core accretion can still operate in the outer disk, but the path to a stable planet often requires migration to the circumbinary region where gas and solids can shepherd a growing core into a locked orbit around the barycenter. If a planet's orbit is significantly inclined relative to the binary plane, gravitational interactions can drive cycles that alter its eccentricity and inclination, though dissipative forces in the disk and subsequent tidal interactions tend to damp extreme tilts and align the planet with the binary's orbital plane over time. Overall, binary systems demonstrate that planet formation is robust under a broader set of gravitational scaffolds than a solitary star would suggest, producing worlds that are both dynamically intriguing and observationally rich. Circumbinary planets, formation, and orbits. Two suns produce a time-varying gravity field that shapes every orbit. A planet in such a system feels the pull of both stars as they orbit each other, a dance that changes with the stars' positions. In the early disk, the binary's gravity clears an inner cavity of gas and dust, pushing planet-forming material outward. Thus, circumbinary planets typically start forming farther from the pair than planets around a single star. Core accretion or pebble accretion can build a core even in these perturbed disks, followed by gas capture if conditions allow. Yet the binary stirs up high relative velocities among planetesimals, making collisions destructive. Gas drag and the aerodynamic pileup of solids and pressure bumps can help growth, but success depends on disk density, temperature, and the binary's eccentricity. Over time, a growing body can migrate inward via interactions with the gas disk, eventually approaching the region where stable orbits survive. In some cases, planets become trapped in resonant configurations with the binary or with each other. Most circumbinary planets orbit in roughly the same plane as the binary. The gravitational influence of the two stars creates a practical inner edge to stable orbits, below which regular alignment becomes unlikely. That boundary moves with the binary's mass ratio and eccentricity, so a more elongated binary pushes the safe region farther outward. Planets emerging beyond this critical radius tend to have moderately circular orbits, though perturbations can pump eccentricity over time. Some systems show gentle oscillations in inclination that keep the planet in a near-coplanar path. Kepler 16b and Kepler 47b illustrate that calm, stable circumbinary orbits are not only possible, but common under the right conditions. Kepler 47 also hosts more than one planet, demonstrating that multi-planet circumbinary architectures exist. Observational techniques such as transit timing variations and eclipse timing provide clues to these planets' masses and orbital layouts. Habitability around binary stars depends on the combined luminosity and the planet's distance from both suns, plus long-term climate stability under the star's motion. Future surveys and improved simulations will sharpen our sense of how circumbinary worlds form, migrate, and endure. Climate and habitability in binary star systems. In the double suns of eternity, planets orbiting the pair illustrate a climate shaped by two suns. Planets in binary systems receive light and heat from two suns, creating a more intricate pattern of insolation than single-star worlds. Circumbinary planets, which orbit around the pair, and planets that stay near one star experience different regimes of irradiation. These arrangements matter for habitability because the timing and intensity of sunshine affect surface temperatures and atmospheric dynamics. As the two stars move through their orbits, the combined insolation can rise and fall in ways that are not seen on solitary star worlds. Two sunrises can occur during one planetary day when both stars are above the horizon, boosting warmth briefly. On circumbinary planets, the habitable zone can shift with the binary phase, creating windows of warmth and cooler spells. With realistic greenhouse effects, climates can remain temperate across substantial flux. Tidal forces from two suns can influence a planet's rotation and axial tilt, shaping climate stability. Obliquity matters. If a world maintains a moderate tilt, seasonal contrasts can be robust, yet manageable, while very small tilts risk long cool spells. Atmospheric circulation can redistribute heat, smoothing some extremes, but sometimes amplifying them through cloud feedbacks. Dual-star radiation changes atmospheric chemistry, including photolysis rates and ozone-like shielding, which in turn affects surface UV exposure. Life might adapt pigments to the light from two suns. In practice, climate stability over long timescales matters, and planets near the inner edge of the binary habitable zone face pronounced oscillations. Researchers combine climate models with orbital dynamics to assess whether oceans can stay temperate and clouds provide a stable climate balance. Observations, data, and methods for studying binary worlds. Binary worlds show that planets can form and survive in the gravity of two suns. Circumbinary planets transit their combined light in ways that reveal the complex dance of two stars in a distant world. Kepler 16b and Kepler 1647b stand as concrete examples of such systems discovered by transit observations. The transits do not occur at a fixed interval because the stars move along their orbits and shift the planet's path across the light source. This leads to irregular timing and durations that encode the geometry and dynamics of the trio. To study these systems, researchers rely on high-precision photometry from space and precise spectroscopy of the host stars. Light curves show dips when the planet crosses the stellar disk, and radial velocity measurements anchor the masses and motions of the stellar pair. Transit timing variations and transit duration variations arise naturally from the three-body dynamics and provide powerful constraints on the planet's orbit and the binary's parameters. Long observational baselines from missions like Kepler and TESS enable the detection of multiple transits and help separate planetary signals from stellar noise. Direct imaging remains challenging for close circumbinary planets due to brightness contrasts and proximity, so most robust results come from timing and light curve analyses. Modeling circumbinary systems demands photodynamical approaches that couple orbital dynamics with light curve synthesis. One integrates the gravitational motion of both stars and the planet, then predicts the exact times and shapes of transits to be compared with data. Bayesian inference, often via Markov chain Monte Carlo or related methods, explores the parameter space and yields probabilistic constraints on orbital elements, inclinations, and stellar properties. Practical hurdles include dilution of the planetary signal by two bright stars, activity in spots on the stellar surfaces, and the need to account for limb darkening on two stellar disks. Multiband photometry and spectroscopic disentangling of the stellar spectra help separate the planetary transit signal from stellar variability and improve mass and radius estimates. Future work expands the census of circumbinary planets with a combination of techniques. Microlensing surveys add distance and orbital geometry regimes not easily accessible by transits, helping map the population beyond the reach of current photometry. Astrometry from missions like Gaia has the potential to detect subtle wobbles induced by planets around binary stars, complementing radial velocity and transit data. Studies of circumbinary disk evolution and planet formation provide context for how such worlds come to be and endure in dual-star environments. In practice, robustly characterizing these systems relies on coordinated, multi-wavelength campaigns and careful treatment of dynamical signals so that the stories told by light curves faithfully reflect the gravitational choreography of two suns and their planetary companion. Implications for science and exploration. Binary star systems host planets that orbit both stars, a configuration known as circumbinary planets. The combined illumination from two suns creates a highly dynamic insolation pattern that shifts as the stars move and as the planet traces its own orbit, shaping temperature swings, weather patterns, and potential habitability. Stable orbits generally lie outside the close, unstable region near the binary. Planet formation around binaries faces a harsher disk environment and different migration histories, which can influence where planets end up. The habitable zone in such systems is not a simple ring. It is shaped by the spectra and variability of both stars and by the gravitational tug of the binary. Observations by Kepler revealed several circumbinary planets, proving that stable planets can exist in these systems. Transits occur against a moving target as the binary orbits, producing irregular, offset timing that helps confirm the planet but complicates simple models. Radial velocity signals from the host stars are muddled by their mutual orbit, requiring long baselines and sophisticated disentangling. Spectroscopic observations must separate light from two stars and a planet's faint signature, demanding high-contrast instruments and careful stellar characterization. These factors make circumbinary planets a proving ground for next-generation detection and analysis methods. For science and exploration, the climate and climate-driven geology on such worlds would be influenced by the dual-flux environment. Seasonal patterns would be irregular due to two suns, and eclipses by the stars could produce dramatic, rapid energy changes. If life exists, photochemical processes could differ widely from single-star worlds, affecting atmospheric biomarkers and biosignature interpretation. From an exploration standpoint, remote sensing would aim to characterize atmospheric composition, surface conditions, and potential oceans through multi-wavelength campaigns. Direct sample return remains speculative, with current technology focused on remote sensing and, in the far future, robotic probes. Kepler 16b and Kepler 47 systems illustrate real circumbinary planets and a path for future studies. Kepler 16b demonstrated that a planet can stably orbit a binary on a timescale long enough to harbor climates, while Kepler 47 shows multiple planets in a single circumbinary system. Nearby binary twins, like Alpha Centauri AB, provoke discussions about whether a distant circumbinary planet could exist, guiding future search strategies. Ultimately, the double suns of eternity frames a scenario where science pushes toward two-pronged exploration, advancing instruments capable of disentangling binary light and designing missions resilient to variable insolation. Today's journey through the double suns of eternity showed how planets can orbit around two suns, creating circumbinary worlds that dance under the gravity of both stars. We outlined the main orbital regimes, circumbinary orbits that stay stable around both suns, planets that ride near one star while feeling the tug of the other, and the resonances that keep these systems from flinging planets into space. We explored how two suns shape day-night cycles, seasons, and climate, and why some binary configurations place a habitable zone where life might plausibly take root. Real discoveries, like Kepler 16b, prove these worlds aren't just fiction, they're real laboratories for gravity and light. If you've ever looked up at a sky painted by two suns and wondered what that would feel like, you're part of this exploration. Curiosity and imagination are what connect us here. If this sparked more questions or ideas, drop them in the comments and consider subscribing to follow the journey. If you enjoyed the episode, give it a like and share it with fellow space dreamers. In the next videos, we'll dive into how astronomers detect circumbinary planets, what the latest discoveries teach us about stability and climates in binary suns, and we'll even walk through how to build a plausible binary world concept for your own stories or games. There's plenty more to uncover in the double suns of eternity. Until then, keep looking up and keep wondering.